Sketch a graph of the inverse of each exponential function. Part A, f of x equals 4 to the x. Alright, first of all, here's f of x. It's going to look something like it's going to go up real fast. Okay, so this actually doesn't touch the x-axis. It's just asymptotic there. And see, so when x is 1, we got f of x. So f of 1 is 4. 1, 2, 1, 2, 3, 4. So there should be a point there, so I kind of missed it. When x is 2, f of x is like 16. So it's way up here. So it actually goes up really fast. Like that. When x is negative 1, f of x is 1/4. Negative 1 comma 1/4. And when x is 0, it crosses right here. The y-intercept is at 1. Right, because f of 0 is equal to 4 to the 0, which is equal to 1. Now for the inverse function, there are a few different ways. Since we're starting off, I'll do it the one way. Y equals 4 to the x is f of x, but we're going to change the f of x to y. So the inverse function would be x equals 4 to the power of y. Now when y is equal to 0, x is equal to 1. Let me do that in, let's say, blue. So there's that. When y is equal to 1, that means x is equal to 4. So when x is 4, right here. And when x is 16, that's because y is 2. And so it goes up to 2, and 16 is right around here. And it goes off. And if you notice in this case, there are no values of x that are going to be negative, because there's no value of y that can ever make 4 to the y equal x if x is negative. Right? So for example, if I put x as negative 1, well, there's nothing that y can equal for that to be true. So that's just going to be there's just nothing in that domain there. So x can never be negative 1. It can't even be 0, actually. It's going to have an asymptote. This is going to have a vertical asymptote here. Okay, if you notice, these guys are symmetrical about the line x equals y. For every x value before, we now have a y value. So we had 0, 1 there. This time we have 1, 0. Here we had 1, 4. This dot right here was 1, comma 4. Well, here we have 4, comma 1. Inverses of each other. Now the other way to write that, which is a new thing we're introducing now, is y equals the log with a base of 4 of x. And that here is also another way to write this, the equation of this function right here, this new function. So the log, if I let x right here be 4, we can say the log of 4 to the base 4 is equal to 1. So we're basically, this equation right here is basically asking the question, 4 to the power of what will give me this x value? Right? So if the x value is 4, 4 to the power of what gives me 4? And it's 1. It's another way of saying, let me take this y equals 4 to the x, and I want to do the inverse operation. I want to know what x value will give me 4. What x value will give me 16? What x value will give me 64? Well, the x value that gives me 64 is 3, because 4 to the power of 3 equals 64. So this log, if I put a 64 here, I'm basically saying what x value will give me 64, and it would be 3. So in this case, we're switching it to make the y value equal to that x value. All right, let me remind you, when we were talking about the sine curve, we had, let's say, when x is pi by 2, we had f of x was equal to 1. Pi by 2 comma 1. But what value of right here would make this sine value f of x. So this is f of x equals sine x. And so I know if I plug in a pi by 2, we all just went through this. For the x, we know that the f of x will be equal to 1. But what if I want f of x to equal 0.8? Well, what is that x value so that f of x is 0.8? Well, what we did is we used the sine inverse. So we made a new equation. Let's call it g of x. Shouldn't call it f of x. G of x equals sine inverse of x. And sine inverse of x would just be sine x, except going up and down this way, so that it's a mirror image of sine x, and it's mirrored in this xy, in the line x equals y. Now if I plug in an x equals 0.8, which is right here, 0.8, I can look up the different values that would all be the sine, where the sine of x is equal to 0.8. And on your calculator, you just have to put in sine inverse of x. So that's the exact same thing we do with logs. Log with the same base as your exponential is just the inverse. So if I ever have x, so let's say y equals 4 to the x. Let's say I want to know when x is, let's say x and y. Let's say I want to know when x is 3. Well, I just plug in a 3. 4 to the power of 3 is 64. But let's say I want to know what value of x will give me a value of 103. Well, that's not really easy, right? You'd have to do 4 to the power of, it'll be 3 point something. We don't even know what that value is. So there's got to be some inverse operation that we could do so that our calculator could easily give us that answer. And that inverse operation, just like sine inverse is the inverse operation for sine, that inverse operation is the log with the base of 4. And now I could just plug in 103. Y equals the log base 4 of 103. And this answer will be the value. It'll be 3 point something. Whatever 4 has to be raised by to give me 103. And if I go on to here, if you go to 103, right here at 16, we have 16 comma 2. If we keep going really, really far, we can get it to 64, and it'll be 64 comma 3. And then when you get to 103, which is even farther to the right, you're going to have 103 comma 3 point something. I'm not going to bother finding out exactly what it is. That's a skill we're going to learn really soon. All right, part B. Let's just first graph f of x, which equals 8 to the power of x. And so when x is 0, 8 to the 0 is 1. When x is 1, 8 to the 1 is 8. When x is 2, 64. This is already getting very, very big. Let's try negative 1. You're going to have 8 to the negative 1, which is 1/8. Negative 2, 1 over 64. And this is already very, very small. So it's going to start over here. It's going to start really, 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 really small. It's going to cross at 1. And by the time you get to 1, you're already at 8. And by the time you get to 2, you're already way off the charts here. All right. Now the inverse of that, so the inverse, let's go x. Instead of f of x, let's call it g of x. And that's going to be equal to, so the inverse is still going to have a base of 8, but this is going to be the log base 8 of x. Right? So now when x is 1, g of x will be 0. When x is 8, g of x will be 1. When x is 64, g of x will be 2. You can see the pattern. It's just the inverse of this. And I'm going to talk about it a little further after I finish this. So 1/8 is going to be negative 1. and 1/64 will be at -2. So what we're saying is, when I plug into x as 1, right here, we're saying 8 to the what gives me 1. Well, that answer is going to be 0, because 8 to the 0 gives me 1. So that g of x is going to be equal to 0. It's the inverse operation. We're basically saying, if this were 8 to the power of x, what value would give us 1? Right? So if this were 8 to the power of x, what value of x would give us 1? Well, that's the value. When we put in a value of 1 here, that answer is going to be given to us, 0. And so the graph is going to be, well, first of all, it's just going to be a mirror image of that graph over there. But this time we have 1, 0. We have 8, 1. So 2, 3, 4, 5, 6, 7, 8, 1 right here. And then your net, so 2, it doesn't hit 2 until it gets over to 64. So this goes real far this way. And on the other side, it comes down at 1/8, we're at -1, which is right here. At 1/64, so really close to 0, we're at -2. And as you can see, this will never go negative. So your domain is all positive numbers. It can never go down to 0. So there we have it. So this is the inverse. You can say g of x equals the log the base of 8 of x. And that's this graph. All right, part C. Let's do a little table of values. X and f of x again. All right, so when x is 0, we know 1/3 to the 0 is 1. Anything to the 0 is 1. When x is 1, we have 1/3. When x is 2, now we have 1/3 squared, which is 1/9. When x is 3, we have 1/27. Let's go into the negatives. -1 will give me 3, right? Because it's going to be 1 over 1/3, which is 3. At -2, you're going to get 9. At -3, you're going to get 27. Right, so that should be easy. At 0, we get 1. So this is 0, comma 1. At 1, we have 1/3. At 2, we have 1/9. And this 1/27, it gets closer and closer to 0 when x is positive this time. At -1, we're at 3. So 2, 3 right here. At -2, we're at 5, 6, 7, 8, 9 right there. So this is -2, comma 9. And then it just goes off the charts, 27, 81. It goes real high that way. Right, now I'm going to do the inverse operation. Right, so the inverse operation, you have your x, and this is your g of x. Okay, so in this case, our f of x, right here, f of x was equal to 1/3 to the power of x. So our g of x, in this case, g of x is equal to the log with the base of 1/3. Make sure that that 1/3 is low and small here of x. X is on the same level as this word log. You're not going to say log. It's not to the power of x. Right? And you're not going to put the 1/3 up on the same level as log like that. That would be wrong. Okay, the base has to be lower. It's going to be a subscript. So 1/3 nice and small down here. And this x should be on the same level as the log. So write it properly. This is going to be important. You have to follow proper conventions when you write these things. Right? And so when x is 1, g of x is going to be 0. When x is 1/3, g of x is going to be 1. 1/9 will give us 2. 1 over 27 will give us 3. 3 will give us -1. 9 will give us -2. And 27 will give us -3. And our graph will again be the mirror image in this line of this graph. So we're going to go 1, 0 is right here. 1/3, which is right here, comma 1. It's going to be right here. And as we get closer and closer to 0, we're going to get higher and higher. Like that. And on the other side, it's going to cross. When we get to 3, we'll be at -1. Right here. By the time we get to 9, so 4, 5, 6, 7, 8, 9. When x is 9, y will be -2. And when x is 27, so that's going to be off the charts already, we're going to get -3, and we go that way. So as you can see, this is your logarithmic with a base of 1/3. So that's g of x equals the log with a base of 1/3 of x. And your f of x, which is this yellow one, f of x is equal to 1/3 to the power of x. Now both of these have a base of 1/3, and that's why these are inverses of each other. There's definitely no reason for me to do part D. It's going to be the exact same concept as A, B, and C. So you should all be able to do part D no problem. All right, number 2, write the equation of each inverse function in question 1 in exponential form and in logarithmic form. All right, so let's do part A. So we have f of x equals 4 to the x is our original function, and we want the inverse. So let's start with the exponential form. So we're going to rewrite f of x equals 4 to the x as y equals 4 to the x. That's the easiest way. And then we want the exponential form of the inverse. So this is the inverse. The exponential is x equals 4 to the power of y. Okay, so these two are inverses of each other. These two, well, are obviously the same thing. Okay. We could also have written it in the logarithmic form, which is y equals, you get a log, the base is 4, so you put a little 4 here, and you put your x there. These are exactly the same equation. The difference, the reason we would ever write it like this is because we like to get our y by itself, right? If I want to plug in an x value, you don't want to know what 4 to the power of y equals. Let's say I plug in x is 100. I don't want to know what 4 to the power of y equals. I want to know what y equals. And so how do you bring this 4 over to the other side? Well, the answer is you do the inverse of that operation, which is the log x to the base 4. So another way to say it is these two equations are just a rearrangement of each other, right? But this is the best arrangement right here because your y is by itself. And if you notice all the functions that we do, we like to keep the y by itself, right? So now that it's written with y equals log x, if you want to, this does happen to be a function, by the way, so we can say g of x equals the log base 4 of x. If you remember the graphs I did before, y equals 4 to the x goes like this. This passes the vertical line test, right? Any vertical line, any x value you put in, you only get one y value. Well, its inverse operation, which is y equals the log of x with the base 4, this also passes the vertical line test. So you can also call it g of x. Remember, f of x, g of x, h of x is something that's reserved only for functions. So you have to make sure it passes the vertical line test before you can name it f of x, g of x, h of x. It's kind of like a symbol to your reader that they can trust that they're going to get only one answer each time they plug in an x value. All right, part B. We've got our original f of x equals 8 to the power of x. I'm just going to write y equals 8 to the power of x. And by the way, this could also be written as x equals the log of y base 8, right? And so that's the original. And our inverse, which is what we're supposed to do for this question, will be x equals 8 to the power of y, or we could have said y equals the log, the base of 8 of x. Or we could rewrite that as, since this is a function as well, we could rewrite that as g of x equals the log of x base 8. Now, I keep saying this is allowed just because it is a function. I want to differentiate what we used to do. So if I did y equals sine x and I asked you to find the inverse, so let's make this the original, and I wanted the inverse of that, okay, that would be x equals sine y, or we could say y equals the sine inverse of x, right? Now this original one, I could say f of x equals sine x. That's no problem because this is a function. But I cannot say g of x equals sine inverse of x because this is not a function. If you remember, the graph of sine x is a repeating, like a periodic function. Well, that means that its inverse goes like this, and this inverse would not pass the vertical line test, so you're not allowed to call it g of x. You can say y equals sine inverse of x, but you can't call it f of x or g of x or h of x. And so that's why I like to mention we can call this g of x equals the log of x with the base 8, but we can only do that because it is a function. It does pass the vertical line test. Part C, f of x equals 1/3 to the power of x. We'll also say y equals 1/3 to the x. That'll make it easier to convert. Let's make the inverse. Oh, by the way, I could also call this the log. I could say x equals the log base of 1/3 of y. These are if I graph these guys, they're exactly the same thing. If you put this into Desmos, you're going to get the exact same graph for all of them. The most convenient, though, is going to be this one. Actually, probably this one. These are the same thing, but I like the f of x because then you could just, if you want to plug in a 2, you could just write f of 2. For the y equals 1/3 to the x, you have to say at x equals 2, y equals 1/3 to the power of 2. Whereas for f of x, you just write f of 2 equals 1/3 to the 2. So this is my favorite right here. Okay, this one's no good because you're plugging in an x value and then you have to take this whole thing apart before you can actually find your y value. Remember, x is your independent variable, so we're always plugging in an x to get a y. So this equation is not the most fun equation to work with. All right, let's do the inverse for all of those. So the inverse, instead of y equals 1/3 to the x, you're going to get x equals 1/3 to the power of y. Or we can say y equals the log, the base of 1/3 of x. And since that's also a function, we can say g of x equals the log base 1/3 of x. And this is the one that's the most convenient of the three of them because we just plug in an x value and we're going to get the answer. I'll just let you do part D on your own. All right, number 5, write the equation of the inverse of each exponential function in exponential form. All right, so A, y equals 3 to the x. It's just going to be x equals 3 to the power of y. B, y equals 10 to the power of x. It's just going to be x equals 10 to the power of y. C, y equals 1/4 of the x equals 1/4 to the power of y. And D, y equals m to the x. So you're going to get x equals m to the y. As you can see, these are all in exponential form, and they're definitely the inverse because we switched the x and the y values. All right, number 6 says, write the equation of the inverse of each exponential function in question 5 in logarithmic form this time. All right, the logarithmic form. So for A, we're going to say y equals the log with the base 3 of x. B, y equals the log base 10 of x, but if it's base 10, you don't have to put base 10. Log of x. It's just assumed that it's base 10. C, y equals, log with the base of 1/4 of x, and D, y equals log base m of x. Alright, number 7, write the equation of each of the following log functions in exponential form. Alright, A, so y equals log, so it's base 5, so we're going to say 5 to the power of y equals x. This is exactly the same as that. It's just a different form. The most convenient form is obviously part A, because x is our independent variable, so we always want the dependent variable to be by itself, right? So even though this gives me the exact same graph, it's not as convenient, because when I plug in an x, let's say I want x to be 42, well, I don't know what to put in my calculator to find y. But if I have it in this form and I let x be 42, well then in my calculator I just plug in the log of 42 with the base of 5, and it will give me my y value, right? And that's the value that you can raise 5 to the that y value is the thing that's going to give you 42, right? So this is actually the most convenient. For some reason they want to know the other form. Let's do part B. Alright, so we see that our base is 10. We're going to raise 10 to the power of y, and that's going to equal x. C, the base is 3, so we make sure we keep our base of 3, and we're going to put the y here and the x there. For D, you just basically switch where you see it here. You just kind of switch them, but you make sure that the base is the same. Let me see without my glasses here. It looks like it's 1/4. So the base is 1/4. And since this is an x above the 1/4, we're going to make it a y, because we're switching it to the other form. There we go. There is the exponential form of those 4 logs. Alright, part 8, write the equation of the inverse of each log functions in question 7 in exponential form. So it's got to be the inverse of this in exponential form. So first of all, let's just do the inverse of that, not in exponential form. So we're just going to switch the x equals log of y base 5, and then we're going to change that to exponential form. So 5 is the base, 5 to the power of x, so y equals 5 to the power of x. B. So let's first make it the inverse. So the inverse is x equals log. To do the inverse, all you have to do, I'm not going to write base 10 because it's just understood that it's base 10 if we don't write it. So we switch the x and the y to make it the inverse, and now I want to write it as an exponent. So the base is 10, and you do to the power of x, and that is equal to y. Okay, so these, like the base 10 here is underneath the y. When you switch it to exponential form, it's the base 10 here is underneath the x, as you can see. Alright, so part C, y equals log x base 3. If we want the inverse, we're going to do x equals log base 3 of y. And then the exponential version, y equals 3 to the power of x. Keep in mind that these two these that I wrote here are both exactly the same thing. You're going to get all the same answers. It's just the one over here on the left is inconvenient, 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 because the y isn't by itself. You plug in an x and you're not getting an answer, right? Whereas these guys are super convenient. If I plug in an x, then in my calculator I just put 5 to the power of that x, and I get my answer of y, right? So whenever you isolate y, that's always the most convenient of the forms, but it doesn't make them different. It just makes it easier. Now these guys over here are the inverse of those things, right? So they're not going to give you the same answers at all. They'll give you the inverse answers. For example, if I let x be 2 in this one, then y is going to be 25. 5 to the 2 is 25. But if I let x be 2 here, y will also be 25, right? But if I let x be 2 here, oops, this is a different. If I let x be 2 here, well then y will definitely not be 25, because 5 to the 25 does not equal 2, right? It'll be like 0 point something. All right, so last one, part D. So first I'm going to give you the inverse operation. X equals log with a base of 1/4. Notice I put that 1/4 down nice and low to show you that it's the base. With a log, the base is a subscript. Right? It's not a superscript, and it's not the same level as log. It's got to go underneath, like kind of at the bottom part of the G there, of y, and the y goes on the same level as the L, the O, the G, and the X on the left there. Right? I don't want that y to be up here. That's not how it's written with logs. Right? Now as an exponential, now all of a sudden the 1/4 does go on the same level as everything else, and we've got our x up here and our y on the same level as the 1/4. So now the x must be a superscript. So this 1/4 is a subscript. The base is a subscript with when you have a log, and when it's an exponential, your exponent is a superscript. All right, number 9, evaluate each of the following. So log of 4 base 2. So basically we're saying 2 to the what gives me 2? The answer is 2. So A, log of 4 base 2 is equal to 2. Because 2 squared equals 4. Part B, log of 27 base 3 is equal to 3. Because I say 3 to the what gives me 27? It's 3 to the 3. So the answer is 3. Notice the base is the same. The answer is this, and the exponent is that. Okay, part C. Log base 4 of 64. So basically we're asking 4 to the what gives us 64, and the answer is 3 as well. That's because 4 to the 3 is equal to 64. Therefore this must equal 3. Right? When we're doing the log, we're basically saying, hey, when I have a base 4, what exponent will it be to give me an answer of 64 in the with the exponential form? Right? Remember, it's an inverse operation. We use logs when it's a time where we're trying to find, hey, what is that exponent that we would be looking for? Right? So whenever we have a question of that's something like, 2 to the p equals 19, and you're like, oh, I don't know, 2 to the 4 is 16, and 2 to the 5 is 32. It's somewhere in between there. So that's when you're going to do the log, and the base is 2, so you're going to put a base of 2. And now you put your 19 here, and that will be your answer for p. And so this you can put in your calculator and give yourself an answer of p. Part D, let's see, we got log of 1 base 5. So it's saying 5 to the what gives me 1? Well, that's going to be 0, because 5 to the power of 0 equals 1. So it doesn't matter what the base is. Whenever you have the log of 1, it's always going to equal 0, because the answer is always whatever this is to the 0 is the thing that gives us 1. With exceptions, right? You can't exactly do 0 to the 0, right? That wouldn't work. So logs have a limitation to what could be in the base, and also what could be what you can take the log of as well. Right? You can never do the log base 5 of -3, because there's nothing, if you do the graph of 5 to the x, the answer is never negative. So there's never a thing that I could let x be to give me a negative number. So there are limitations in the domain for the log functions. Part E. So we're going to say log, there's a base of 2, 1/2. So 2 to the what gives me 1/2? Well, that would be -1. right? So the answer can be a negative, right? Because your domain in an exponential can go into the negatives, right? Which means your log function can have an answer that is in the negatives. You just can't plug in anything less, like that's 0 or less, right? So this number here can never be a 0 or less, but your answer can be a negative. We'll work with that enough so that you'll get the hang of that. And lastly, log base 3 of the square root of 3. So we're saying 3 to the power of what equals root 3? Well, that's just 1/2. We already know our rules that, let's erase this here. So we know our rules that 3 to the power of 1/2 is equal to the same thing as the square root of 3. Therefore, the log base 3, so 3, this is saying 3 to the what gives me root 3? Well, it's 1/2. All right, number 10, why can log of -9 base 3 not be evaluated? Well, that's what I was just talking about when I was doing number 9. So we're saying 3 to the power of what equals -9. Well, here's the graph of 3 to the power of x. And it goes like this, off to infinity, that way, and that one goes, has a horizontal asymptote at y equals 0. If you notice, there's no x value. If I plug in x is 0, I get 1. 3 to the 0 is 1. Right? X and 3 to the x. Right? If I put in a 0, I get 1. If I plug in a 1, I get 3. If I plug in a 2, I get 9. Well, that's certainly not going to be -9. But let's start putting in negative numbers. -1, I get 1/3. -2, I get 1/9. -3, I get 1/27. Right? So no matter what direction I go, I will never get a y value that's in the negative numbers. So there is no answer for this. You cannot evaluate it. Number 11, for each of the following log functions, write the coordinates of the 5 points that have the y values of -2, -1, 0, 1, 2. All right, to do that, let's just make a table of values. I have an x and a y, and I want the y value to be -2, -1, 0, 1, and 2, and I need to find those x values. Let's start with part A. For part A, we have y equals log of x base 2. All right, so for this one, we're saying that the y value is -2. So we're saying -2 equals log of x base 2. Now I could switch this into an exponential. The base is 2, and that's the -2 goes here, and the x goes here. So basically I'm saying x is 2 to the power of -2. Well, 2 squared is 4. 2 to the -2 is 1/4. So the x value must be 1/4. Right? So for the second one, we're saying -1 equals the log of x base 2. Well, let's change that to an exponential to make it easier. So we can say, we know the base is 2, so let's keep the base of 2. And the -1 goes over here, and the x goes over here. So it's kind of like, it's not actually switching, but in my brain I always think, it seems to me that this looks like a little mini exponential here. But if I want to take the log out of there, I've got to switch. The base does stay the same of 2. The base will never change. And then the -1 ends up going over there, and the x goes over there. So I kind of think of it as a switcheroo. If I switch from exponential to a log, or a log to an exponential, I always keep the same base first of all, and then I just switch those two. In my brain, that's what I'm doing. That's not the technical thing that's happening, but that's okay. So x is 2 to the -1, which is just 1/2. 1/2 can go here in the table of values. All right, let's do the third one. So again, we're replacing the y value. Right, y value is going to be 0. So there's my equation. I'm going to say 0 equals log of x base 2. I'm going to switch that to an exponential. I'm not going to do the inverse operation. I'm going to keep the exact same. I'm not doing the inverse function. I'm keeping the exact same equation here, but I'm going to change it to an exponential. So the base is still 2, the 0 goes here, and the x goes there. It's just a more convenient way to do it, and that is equal to 1. All right, let's do that again. 1 equals log of x base 2, which means 2 to the power of 1 is equal to x, so that's just 2. And the last one we can do over on the left here, so we're going to let y equal 2, so 2 equals log of x base 2, and that means that 2 to the power of 2 equals x. Remember, keep that same base, and so x is 4. And that makes sense. If I plugged in a 4 into here, I'm going to over here, let's say y equals log x base 2. If I plug in a 4, I'm getting y equals log of 4 base 2. Yeah, we're saying 2 to the what gives me 4, and that is equal to 2. And so here, that does give me a value of 2. And let's try it for 1/4. Y equals log base 2 of 1/4. We're saying 2 to the power of what gives me 1/4, and that would be -2. And so that makes sense. That's verifying our answer there.